Alright, so today we're going to learn about Karnaugh maps, otherwise known as K-maps. So let's get started. So we'll first learn what a basic K-map is, and then we'll learn how to expand that K-map to make it more useful. So Karnaugh maps, otherwise known as K-maps, can be used to simplify Boolean expressions in place of simplification rules. I did another video on those simplification rules if you want to see them, but they won't be necessary for today thanks to the K-map. So at the bottom, we have an example of a two-variable k-map for the initial expression of a or a and b. So we see that initial expression on the left, and there's a truth table for it there next. And then the arrow is next pointing to what the k-map is. So the left column and the top row, they represent the possible input values, while the intersections represent the corresponding output values. So you'll see for the A column where it's 0 and the B column where it's 0, where it intersects, um, that's also 0, just like in the truth table. So yeah, once you have all your outputs mapped out, what you're going to do is group all the adjacent ones together to get a final expression based on what variables remain constant in the grouping. So if we go out here, get a better look at this, we have the outputs mapped out here, and there's two ones here at the bottom, so we group them together, and we pay attention to which of these stays constant. So the B doesn't, because it's going 0 and 1, but the A does, it's only 1. So that's why, in this case, the simplified expression would be just A. All right, some additional notes on K-maps, which you want to know, is that all the ones in the K-map must be accounted for at least once. They can be accounted for more than once, depending on how you group it, but at least once. To get the most simple expression, you should look for the largest possible adjacent groups. However, you must note that those groups must be powers of 2. It can't be like groups of 3 or 5 or whatever. And those groups can also be found across edges. So if you had a 1 on like the top left corner of a K-map, and you also had a 1 at the top right corner of a K-map, you could group those together, and we'll see some examples of those. And K-maps, they aren't really particularly useful for the two variable expressions like we saw before. You could have just easily figured that out yourself probably without even looking at it. But they become more useful when you use them for 3 or 4 variable expressions. And at that point, if you do like 5 or more, it starts to become too much of a hassle for a reason we will see shortly. So yeah, that we're going to talk about expanding now to 3 variable K-maps. So when adding a third variable, there will either be twice as many columns or twice as many rows, depending on what side you pick to have the two variables together. So below we have an example of a 3 variable K-map. I just noticed I misspelled 3 as Z. Right? Anyway, so we have another truth table there at the bottom left, and we have the corresponding K-map. I decided here to use AB as a column and C as our top row. So yeah, we see the column for the AB. We count for all the values, but you might notice that it goes 0, 0, 0, 1, which is good so far, what you would expect. But after that, it goes to 1, 1, then 1, 0, which is the opposite of what you'd expect. You'd expect that 1, 0 to become before the 1, 1, and we'll talk about why that is in a second. But if we just look at how the ones here are all grouped together, we see that the bottom half can all be grouped together as a group of 4, and the thing that's constant here is A. A is 1, so that leads us to our final expression of having A here, but we also have the ones up here we need to account for, and those can be connected to the ones at the bottom here in another group of 4. And in this case, you'll see that the B in for all 4 of these is going to be 0, and that leads to the B knot here. which gives us our final expression of A or inverted B. So yeah, as I was saying, you may have noticed that in that leftmost column that the 0, 1 changed to 1, 1, then to 1, 0, which is the opposite of what you may have expected based on the order in the truth table. And the reason for this is because K-maps actually use gray code. And the idea of gray code is the idea of binary number sequences only changing one bit between each value. So that 0, 1 changes to 1, 0, or 1, 1, because it's that first 0 is changing to a 1, and then the 1, 1, that second 1 is changing to a 0. Instead of if you did 0, 1 to 1, 0, that's both bits changing, which would violate the gray code. And the reason we do this is actually because it ensures that when you group all the adjacent ones, that'll get the most simplified expression. So yeah, with this in mind, let's expand to a 4-variable K-map. So here's a 4-variable K-map, and we're going to note how using the gray code will help us give us our simplified expression. So yeah, we have a pretty lengthy truth table here with lots of values, and we have our K-map there to the side, right side, and we see both have 2 of the variables in there. So we have a kind of 4x4 there to account for all the values, and so with these groupings, these middle values all are 1. Thanks to the gray code, actually, this is an example of the gray code coming together, because if it was these two were switched, then you wouldn't be able to group like this. But we can, so that helps us give our simplified expression. So these 8 ones can be grouped together, and the thing that remains constant between all of these is that B here is 1 for all of them. So we can simplify this group down to just B. And again, if you look at the sides, they're all 1, so you can group them together in their own group of 8, and the thing that remains constant between all 8 of these is that the D is 0, so that gives us the inverted D as our second term, which gives us our final expression here of B or D inverted. Alright, so for our practice today, I want you to use K-maps to simplify the following. So first we have an initial expression, and then second we have a truth table. And here's a little hint. For the first one, you're going to want to make it into a truth table, like the second one. And the only difference there and that at that point would be the fact that the top one has 3 variables instead of 4, like the bottom one. So pause the video now to do these yourself, because I am going to start going over the solutions in 3, 2, 1. So first, looking at this initial expression, so as I hinted, you're going to make a truth table. So if you follow this initial expression to where your 1s should be, you'll get this truth table with 5 of the outputs being 1. And from there, you should be able to pretty easily make a K-map. And here's the one I made. So here that is. And then next, you're going to want to identify the groups of adjacent ones to find your simplified expression. So looking at our K-map, you should be able to pretty easily spot that the bottom half is all 1s, so you can get a group of 4 out of that. And if we look at what is constant between all those, we'll see that it is that A is 1, but you also notice that 1 there at the top left. But as I said, you can add a group across edges. So we'll group that with the 1 on the bottom of that column. And the things that remain constant in that case is that the C is 0, and that also the B is 0. Because if you, as I said, bigger groups you get simpler expressions, but when it's smaller, you might still have multiple variables in that term. So that leads us to a final expression of x is equal to A or inverted B and inverted C, which is far more simpler than what we had at the start. So that brings us to our second one, which is this truth table. And since it's in a truth table already, we can skip that first step of making a truth table, since we already have a truth table, and make a K-map. So here's our K-map for it, using our gray code. So yeah, next we will identify the groups of adjacent ones to find our simplified expression. So first, those middle two columns are all 1. So the thing that remains constant in there, the only thing that remains constant in there, is that D is 1. So that'll be one of our terms, but we have these ones at the side here that we need to account for, and we can do that pretty easily by, as we said, you can have an overlap. So you can account for ones multiple times as long as it's to also account for the unaccounted for ones. So we'll do a group here, a group of 4 here, and the things that remain constant here is that B is 1 and that C is 0. And then we'll have another group of 4 here at the top right, and the things that remain constant here is that C is 1 and that A is 0. So that leads us to a final expression of D or B inverted C or A inverted C. All right, so that'll do it. Hopefully that all made sense. If you have any questions, leave them in the comments below. I'll see y'all later.